Hey everybody, in this lesson we're going to apply the Aufbau principle, the Pauli exclusion principle, and Hund's rule to write electron configurations. I've also got a helpful little shortcut called the diagonal rule that makes all of these other principles almost useless. And let's get into it to learn how to write electron configurations. Weirdly enough, writing an electron configuration, which maybe I should back up and say what this really is. We are trying to assign electrons to orbitals. In other words, if an atom has, let's just come up with a random number, 12 electrons, how do you know what orbitals those electrons go into? Would it be the 1s, the 2s, the 3s, the 5p? How are you supposed to know? That's what this is all about, and that's what writing an electron configuration is. We're first going to compare this to something not chemistry, and that is riding a bus. Because as strange as it sounds, putting electrons into orbitals is a whole lot like getting on a bus on your way to school. So the first thing is, where would you sit when you get on an empty bus? Assuming maybe you're super tired, you want to do as little walking as possible, you're going to sit as close to the front as possible since it takes less energy to get there. Why would you walk all the way to the back if you don't have to? How many people per seat? About 2, right? I know some of them are a little bit bigger, but comfortably 2 people per seat. And given the option, do you take the empty seat or sit to someone else, next to someone else? You're going to take the empty seat when it's available. Keeping those same things in mind, so just shrunk them down and put them on the left-hand side of the screen. Let's do the same for atoms. Just like we sit as close to the front of the bus as possible, that same rule is described by the Aufbau principle, which says electrons are going to enter orbitals of the lowest energy level first, synonymous with the front of the bus. Just like it's 2 people per seat comfortably, the Pauli exclusion principle tells us that each orbital can hold only 2 electrons. And lastly, given the option, do you take the empty seat or sit next to someone else? Hund's rule tells us if there's multiple orbitals that all have the same energy, electrons are going to take the empty orbital first. You'll see all of these rules applied in a diagram that is called an Aufbau diagram. We're going to draw a simple one together first. The Aufbau diagram, you can think about it as essentially a map of a school bus, but instead of seats, they are representations of orbitals. Rather than drawing all of the complex orbital shapes, we simply use a line. This line represents an orbital, and we're going to start at the bottom left-hand corner with the 1s orbital. We also need to clarify that there is going to be a ranking here. The lower an orbital appears on the Aufbau diagram, the lower the amount of energy that orbital has. So my 1s orbital is going to be the furthest to the bottom, which means it's also the orbital of the lowest energy value. And as we go up, we're mapping out orbitals with higher energy values. So first is the 1s, a little bit higher in energy, is a different orbital. This time it's the 2s. Also keep in mind we have now entered the second principal energy level, which has the 2s, but it also has the 2p's. Now some things to keep in mind from my last video or from your prior knowledge about orbitals. For the 2p's, there's actually 3 of those, so I have to do 3 different lines. They all have the same energy value, and it's just slightly higher than the 2s. We can label them specifically as the 2px, the 2py, and the 2pz. After the second principal energy level, we'll go up to the third principal energy level, which has the 3s, the 3p's. I'm not going to label them this time as 3px, 3py, and 3pz. We can just summarize them all at once as the 3p's. And there's also the 3d's, which we'll have to add over here. I'm crunching them together a little bit because I'm running out of space, but there are 5 separate 3D orbitals, so I need 5 separate lines. Some of the stranger things here is that while the 3s, 3p, and 3d all make up the third principal energy level, the fourth principal energy level, starting with the 4s, actually kind of creeps its way in here and is just slightly lower in energy level than the 3Ds. And that's as far as we're going to go. If you Google some other Aufbau diagrams online, you'll see a full map of all the orbitals. But for our purposes here, this is enough. So this is a diagram that shows us the energy values of the orbitals so that we can start assigning electrons to them. And actually, let's do that now, beginning with our first sample, sodium. Sodium atoms have 11 protons, which means as long as the atom is neutral, it also has 11 electrons that we have to assign to the proper orbitals. Just like we would sit as close to the front of the bus as possible, the Aufbau principle tells us to fill the lowest orbitals first. So my first electron goes to the first seat, and that is the 1s. In this type of a diagram, we represent an electron with an arrow that is pointing up. That represents a certain property that electrons have called spin up. And we're not going to really talk about what that means. It's not actually spinning, but that is what the arrow represents. So my first electron goes into the 1s. The second electron that gets on this bus, or that we assign into orbitals, still has an open seat, right? The Pauli exclusion principle tells us that each of these orbitals can hold 2 electrons. So right now this seat only has 1 person. It can take a second. The second electron is a second arrow, but this time pointing down to represent the property called spin down. Within a pair of electrons in any orbital, one is spin up and the other is spin down. This orbital is now full. This seat on the bus is now full. The next electron that gets on has to walk further to the back and take the next available seat, the 2s. The fourth electron has an available seat here in the 2s. This one is now full. The fifth electron gets on, now has an option of 3 open seats. So it doesn't really matter what we put the first electron into, we'll start it here. Now the next electron has these 3 equivalent seats, these 3 equivalent energy orbitals to choose from. Our final rule, Hund's rule, says that they're not going to pair up when there are open orbitals available. So my next one takes an open orbital. My next electron takes our final open orbital. And that is Hund's rule in action. Essentially, the electrons are going to spread out, not pairing up until each orbital has 1. Then they're going to pair, then they're going to pair, then they're going to pair. So that's all of our rules applied, and you just keep following those patterns until we get up to 11. So far, I've only got 2, 4, 6, 8, 10. So my 11th electron takes the 3s. And what you've just done is mapped out where all of sodium's 11 electrons are found, exactly what orbitals they are in. Sometimes this can be referred to as orbital box notation. I'm just throwing in some of the different terms that I've seen. So orbital box notation is essentially this, putting in arrows to represent electrons on top of these different orbitals. Another common notation type is the same thing, just written out on one line, which I'm going to do here, rather than this drawing of the diagram and putting in arrows. It can be called spdf notation. Here's how it looks. The first orbital we filled was the 1s. So instead of writing 1s with a line and 2 arrows, we simply write 1s with a superscript of 2. It looks like 1s squared. It's not squared. It's a 1s orbital with 2 electrons in it. And then you just keep listing them out the same way that you filled them. So 1s2. Next place we went was the 2s, which holds 2. Then the 2 p's all combined, which can hold a total of 6. Count them with me, 2, 4, and 6. So the p's can always hold a total of 6. Followed with our last orbital, 3s, which only contained 1 electron. Writing this is a little bit more common in a chemistry class because it's faster and doesn't require you to draw all these lines and arrows. At this point, it's a good idea if you try to do it yourself. First on an Aufbau diagram or orbital box notation, and then again with spdf notation, this time for an atom of sulfur. Sulfur has 16 protons, so that means a neutral atom will have 16 electrons. Let's start putting them in the 1s first. 2 electrons, then another 2 in the 2s. My next 3 spread out across the 2 p's and then pair up after each orbital has 1 electron. This gives me a total of 10, so I've got to go 6 more, 2 of them here in the 3s. Now we're in the 3p's where my electrons will spread out like so until finally I fill up my 3p's. Now, if you're counting along with me, you might have noticed something. Sulfur only has 16, and I put in too many. This was 2, 4, 6, 8, 10, 12, and with these 6, that puts me up to 18. So I didn't need to do all those. Let's erase some of these and back up and actually pay attention to how we do these 3p's. So at this point I had 12 electrons added in. I have to do just 4 more, and it really matters how you put them. 1 electron in an empty orbital, next electron in an empty orbital, next electron gets an empty orbital too. They spread out first. It's only my 4th electron that gets paired up, and that is my official total of 16 electrons, and this would be sulfur's orbital box notation. If you're doing this SPDF style, it would look like this: 1s with 2 electrons, 2s with 2, 2 p's all clumped together with 6. My 3s orbital contained 2, and my 3p orbitals only contained 4. Let's try another more complicated one, this time together for a larger atom of nickel. I'm going to fly through my lower energy orbitals first, just to save time. So up to the 3p orbitals, this gives me a total of 2, 4, 6, 8, 10, 12, 14, 16, 18 total electrons for nickel. I have to get that total up to 28, so I've got 10 more to do. I'm stopping here because something strange happens. After the 3p's are full, you might think that the 3d's are the next place to start putting electrons, because we're going to fill that whole 3rd energy level first. But the weird part is that's not what happens, because the 4s is actually lower in energy than the 3d's. So even though it's in the 4th energy level, according to the Aufbau rule, we're going to fill the 4s orbitals first and then go back into the 3d's, where my electrons are going to start spreading out before they pair up across all 5 this time, just like we did in the 3p's. My 4s's were 20 electrons, so this gets me to 25. To get up to 28, I need 3 electrons paired up in these orbitals here. Finally, I've got 28 total electrons, and that is the orbital box notation of nickel. If you were to do this in SPDF style, it would be all the same stuff, but just listed out in this way: 1s2, 2s2, 2p6. Let's speed through some of these. And while I have run out of room here, the last one would be 3d8. Alright, 2 more things for this video. One of those is one final example for you to try, this time rubidium. Try the orbital box notation on the Aufbau diagram, and then try an SPDF notation. Ideally, you should pause the video and click play again to watch me go over the answers. So rubidium has 37 total electrons. That's a pretty big one. I'm going to go ahead and start throwing those in here, starting at the 1s. And I'll stop at the 4p's because that is a total of 36 electrons, which means I just need 1 more that ends up in the 5s orbital. In terms of SPDF, if you listed all those out, they would be the same except written this way: 1s2, 2s2, 2p6, and finally ending with 5s1. So if you can do rubidium, then you pretty much can write electron configurations. There's just one last thing that everybody should know, and that is, what about if you did not have the Aufbau diagram? If you didn't have this nice little map that kind of tells you which orbitals for the electrons to go into, how could you go about this same process, especially when it comes to things like knowing that the 4s gets filled before the 3d, and then you're back to the 4p, then to the 5s. The order gets very hard to remember in these higher energy levels. Luckily, we have a trick for that, and it's called the diagonal rule. It still takes a little bit of memorization on your part, but if you can write this out, it's going to always give you that electron filling order. Here's how it works. You want to start with a piece of lined paper to keep everything nice and neat, and begin at the top with the 1s orbital. Beneath the 1s, you'll start listing the second principal energy level, which contains the 2s, and you want to keep it directly in a column with the 1s, and then start adding each additional orbital each time, now in the same line. So 2s and 2p. Directly beneath that, we'll repeat 3s, 3p, and add a 3d. Beneath that, 4s, 4p, 4d, this time adding the 4f. Once you get to the f orbitals, you don't have to worry about adding any new orbital types. You can stop at the f's for as many energy levels as you need. For this example, I'll go to the 7th energy level like so. So while you still have to remember how to set these up, you can see just how fast and easy it is to do that. It's called the diagonal rule because the final step is to draw diagonal arrows through each orbital, and these are key because the arrows give you the order in which you fill electrons. For example, my first arrow goes through the 1s orbital because that's the first orbital I put electrons into, followed by my second arrow, which goes through the 2s, then the 2p, then the 3s, and here's where it gets really helpful, then the 3p, followed by the 4s. After 4s, you would fill the 3d, the 4p, and the 5s. Remember how we did it for rubidium, the 3d, the 4p, and the 5s. My arrow tells me that without the Aufbau diagram, and this works as high as you need it to go. 4d, 5p, 6s, 4f, 5d, 6p, 7s, and so on. So this is a very helpful memory tool that you are going to want to memorize when it comes to writing electron configurations. That also wraps it up for this video. Thanks a lot for watching.